Good afternoon, everyone. Welcome back to the tutorial 9 of surface water hydrology. In this tutorial, we are going to do problems on flood routing. You may have gone through the video lectures that were uploaded last week. So I will give a quick recap of first what has been uploaded, and then we can do the problems. So starting with the flood routing. Flood routing is a technique through which we can find the hydrograph at the downstream section. So let's say you have a river. This is your upstream section, and this is your downstream section. If you know the inflow hydrograph, you can compute the hydrograph at the downstream section. So in short, we can say this is type of forecasting the hydrograph at the downstream section by knowing the hydrograph at the upstream section. Now, once the if you route, this is called a routing, and if you route this flood hydrograph from upstream to the downstream section, so two things happen. One is that the peak that you get, peak discharge. So let's say you have this inflow hydrograph, this one, and this is your outflow hydrograph. So the inflow hydrograph has some peak, and outflow hydrograph will also get some peak. The difference in this peak is called attenuation. So what actually happens from upstream to the downstream? Your peak of hydrograph gets decreased. So this is called attenuation. And the second thing, what happens is the time at which this peak occurs. Timing of peak. So initially, let's say for the inflow hydrograph, this peak was attained at time t1. Now for the outflow hydrograph, this peak of this outflow hydrograph will be at the time t2. So this will be t2 will be always greater than t1, and the time difference is defined as lag. So for any inflow hydrograph, if you are going to predict or forecast, or we can say routing at the downstream section, so two things happen. One is that your peak decrease, which is called attenuation, and also the uh, timing of this peak increases, which is the difference of that timing is called as lag. So now there are two different types of routing when it comes to the uh, structure or the river or channel in which you are doing the routing. So one is called the river reservoir routing and another is called the channel routing. So in the reservoir routing, you try to predict the variation of reservoir's elevation and outflow discharge within the time. So it's to predict the variation reservoir elevation and outflow discharge. While in case of channel routing, so in the channel routing, what we try to do is that we try to study the shape of the hydrograph as it travels through the as the water travels through the channel. So what we try to do is change in the shape hydrograph. This has already been covered in the video lectures, but I am trying to give you a quick recap so that we can start with the problems. And similarly, now when it comes to the type of routing, based on the method which you use, we have two types of routing. One is called hydrological routing, and the second one is called hydraulic routing. So, in case of hydrological routing, this is completely based on continuity equation. And what the continuity equation is, that is the change in storage is inflow minus outflow. And similarly, but in case of hydraulic routing, this is based on uh, continuity equation, but it also uses the equations of motion for the unsteady flow. So another key difference is that here you only try to solve discharge as a function of time. It's very simplistic approach, simple, but yeah, this will be less accurate. While as in this case, in the case of hydraulic routing, you try to solve Q as a function of both time and space. So this is complex. It will take a lot of uh, computational power, but it will be more accurate as compared to the hydrological routing. So any doubts in this case? So if not, then we can start with the hydrological routing. So we first will start with the basic equations. Now let's say we know the continuity equation. You have some, let's say, some storage or something, watershed or channel. So you have some inflow into this and some outflow from the system. So the continuity equation is that change in storage with the time will be inflow minus outflow. So if you have a time step of 2, so we are trying to do between T1 to T2, the continuity equation, then the continuity equation can be written as delta S upon delta T, I bar minus, but this is the average value of I between T1 and T2. Q is the average value of discharge, outflow discharge between time T1 and T2. So delta S, we can write it is I bar delta T, Q by delta T. So this I is your average inflow and Q is average outflow. Delta S will be the change in storage. Now, I bar can be written in short, it's I1 plus I2 divided by 2, where I1 and I2 are the inflow at time T1 and T2. Similarly, Q bar can be written as Q1 plus Q2 divided by 2, where Q1 and Q2 are the discharge at time T1 and T2. So delta S is change in storage, which is S2 minus S1. So this equation we can write it as I1 plus I2 divided by 2 into delta T minus Q1 plus Q2 divided by 2 into delta T. This will be your S2 minus. But it's important to note that this delta T when you will apply this continuity equation for a routing, then this delta should be small. Now, in case of hydraulic routing, the basic equations that we have is, so one is the differential form of continuity equation. Let's say this is your channel having cross section. So this is your depth y and this is your area A. So the continuity equation is V dou y upon dou x plus y dou v upon dou x, where V is your velocity of the flow and this is 0. So one is the, in case of hydraulic routing, the first thing that we use is the differential form of the continuity equation. And the second thing that is used in this case is the equation of motion. But in case of a unsteady flow. And I will write the equation here, dou v upon dou t plus v dou v upon dou x is g times dou y upon dou x minus g s naught minus sf is equal to 0. So now these two equations, in case of hydraulic routing, we use the equation 1 and equation 2. And these two equations are combined called as Saint-Venant's equation. So we need to solve equation 1 and 2 in case of the hydraulic routing. Whereas in case of hydrological routing, we just use the simplest form of the continuity equation. Now we will start with first method of hydrological method of reservoir routing. So now in this case, we use the continuity equation and we try to use the continuity equation for the reservoir routing. And in this method only, we will be dealing with the modified tools method, which is one of the method in through which we can route the reservoir. And I'll start. So this is level pool routing, also it's called level pool routing. So what we know is that the storage in this case is the function of the depth that you have of the reservoir. And similarly, the discharge is also the function of the depth of the reservoir. The So if storage is the function of H and discharge is the function of H, and then we can write that storage is the function of discharge. And but important thing is that this storage, discharge, and you have depth. So these all will vary with time. So they have their dependence on the time. So S is function of time, Q is function of time, and H is also function of time. We can write it as inflow also. Inflow is also function of time. Now the basic continuity equation that we had is ds by dt is equal to I minus q. And when we saw in case of the hydrological routing, this was S delta S is equal to I1 plus I2 divided by 2 into delta T minus Q1 plus Q2 divided by 2 into delta T. So if we use the notations of, for 2 we can use J plus 1 and for 1 we can use J. So then I can write this Sj plus 1 minus Sj. This will be Sj plus 1 plus Sj, sorry, I divided by 2 into delta T minus Qj plus 1 plus Qj divided by 2 into delta T. So this equation we are going to use further in this method. So now let's take a simple case of uncontrolled spillway reservoir. So in this case, discharge can be directly computed using this equation. Where the CDL is constant and the only variable that you have on the right side is the head. This is head over spillway. This is coefficient of discharge. And this is your effective length of spillway. So if you look clearly, the Q is here as function of H that we require in this method, that Q needs to be dependent on the depth of the reservoir. So now if we have to route the reservoir using this hydrological method, so what we need is first as we need a storage versus elevation plot. Then we need a outflow versus elevation plot. And then another thing is that you need to know that value of storage, inflow and discharge at time t is equal to 0. So these are the requirements. Once we know these things, then we can start with the routing and then we can forecast or we can predict the hydrograph at the downstream section. So one such method is modified Pull's method. So if I use the write the equation, it's I1 plus I2 divided by 2 into delta T plus S1 minus Q1 delta T upon 2 equal to S2 plus Q2 into delta T divided by 2. So now the procedure is that I will write, then we can start with the following. First is to prepare a plot of S plus Q delta T divided by 2 versus time. Second thing is we need to plot Q versus H. And the third thing is that the SHQ at time t is equal to 0 should be known. And then hence we can calculate the value of SHQ for t equal to 1 first time step using the equation here. So it is I1 plus I2 divided by 2 into delta t. And since you know the value of I1, I2 and 2, you know the value of S1 minus Q1 delta T upon 2 because the values at T is equal to 0 is known. So once these two are known, you can put the equation and you can get the value of S2 plus Q2 delta T upon 2. Once this value is calculated, you can use the curve here with the time T, and from this you can compute the value of Q, and similarly you can calculate the value of H. And for the fourth time step, what you can do is now you can after doing this, after calculating the value of Q, H and S, you can deduct Q2 delta T, subtracting, I can say, from S2 plus Q2 delta T divided by 2. So you get the value of S1. I can write this S2 minus Q2 into delta T by 2. So for the next time step, this will be S1 minus Q1 delta T upon 2. And then you need to repeat these all steps. In this way, you can get the outflow hydrogram. So any doubts on this one? Because next we are going to do a problem on this. So you are given a reservoir that has following elevation, your discharge and storage relationships also. So this is your elevation, this is your storage, this is your outflow discharge. So when the reservoir levels were at this 100.50, the following flood hydrograph entered the reservoir. You are given the time, you are given the discharge, and you need to route the flood and obtain the outflow hydrograph, the reservoir elevation, and the time curve during the passage of the flood wave. So this has to be done using the modified goals method. So if I write down the steps, and then we can go to the Excel sheet also. Wait a second. Yeah. So, the problem we have. So we know the time step that we have in this problem is 6 hours. So delta T is 6 hours. And if you calculate this into the seconds, so delta T will be 6 into 60 into 60, which will be the value of 216 into 10 raised to power 4 seconds. You can write it as 2.16, sorry, 3 seconds. So it will be 0.216 into 10 raised to power 6 seconds. And the next thing what we need to do is that we need to compute H Q S plus Q delta T divided by 2. And then create a plot for all these what we are required. So one is Q versus H. Another plot that we need is S plus Q delta T divided by 2 versus H. So, but interesting thing that we should first note is that I think let's first plot these on the Excel and then we can start with the further solution. So you are given the elevation and this is your discharge values. I have written here and these are your storage values. So what we need to do is to compute S, which is the storage, plus Q, which is discharge. Q into delta T. Delta T we computed it as values of 0.216. So we need to divide this by 2. So this is your P value 3.35 and drag it down. So the next thing is that we need to plot the storage versus Q versus H plot. And so this is your Q and this is your H. Similarly, another time you need to plot these values S plus Q delta T divided by 2 with the elevation. So let's plot these. So you need to plot on the x-axis, you need to plot s plus q delta t values, and on the y-axis, you need to plot the values of h, which is the elevation. So this is your plot. So this is first plot, which is s plus q delta t divided by 2 versus h. And the second plot that we need is, let's say, b. On the x-axis again, earlier it was s plus q delta t divided by 2. Now it's uh, q, that is discharge, that we will put on x-axis. And on the y-axis, we'll plot the elevation. So this is your q versus h plot, and this is your s plus q delta t divided by 2 versus h plot. Now we can start with the computation. Yeah. So these two plots I have kept here. Now, yes, what's the problem? Sorry for that. Yeah, so we start. So we have at the start of routing, it was given that h is to be 100.5, q value was 10 meter cube per second, and s minus q into delta t divided by 2. If you compute this, so you know the value at the t is equal to 0, value of s cube, and this comes out to be 3.362 million meter cube. So we know from equation s plus q delta t divided by 2 is equal to I1 plus I2 divided by 2 into delta t 9 plus s minus q delta t divided by 2. So if you put the value here and use the value of I1 and I2 divided by 2, we are given. So this is your I1, this is your I for the first time step. So it comes to be 10 plus 20 divided by 2 and 0.0216, plus you have value of 3.362 of this. You compute, this comes out to be 3.686 million meter cube. So now you know the value of s plus q delta t. divided by 2. But what we need to actually find is the value of Q and value of H, so that we can proceed for the next time step also. And this Q will give us the outflow hydrograph. So you take the value of S plus Q delta T divided by 2. So this is the curve S plus Q delta T divided by 2. And this is your value of H. So you have the value of S plus Q delta T divided by, which is equal to 3.686. So 3.868, so it will be roughly here. And you need to find the corresponding on the plot, corresponding H. So let's say this H comes out to be 100.62 meter. I think it's in meters. Once you know the now the value of H, and for the same H you can compute the Q, because this is the curve of Q versus H. So you can exactly figure out here. So this will be the value of Q, and this will come out to be nearly 13 meter cube per second. So once at for time step T1, you computed the value of H and you computed the value of Q. So similarly, you can compute S minus Q delta T divided by 2 for next time step. So this will be the S plus Q delta T divided by 2 of previous day or previous time step minus Q delta T. So S plus Q delta T divided by 2 of previous time step, we know it was 3.868, minus you computed the value of Q now, it's 13, and you multiply this with 0.0216, which is your delta T. You get a value of 3.405 million meter cube. And now using this value, again, you have to repeat the steps. You will put the value of S minus Q delta T here. Now the I1 and I2 for the next time step will be 20 and 55. And you can compute the value of S plus Q delta T again. And from that S plus Q delta T using this curve, you can find the value of H. From the same value of H, you can find the value of Q. And from the value of H and Q, you can compute again this and so on for all the time steps, and you can finally compute the all values. So any questions on this? If not, then I will just give a quick recap of second method, which is similar to the first method only, which is Godrich method. So this is bit a semi-graphical approach. So you have again I1 plus I2 plus, so you rearrange terms in the different way, so that equation becomes like this. So this is going to be your equation. Sorry, this is plus here. And what we need to find is the value of this. So in this case, you first plot OS beta delta T plus Q versus H. So this is going to be the first plot. Second plot will be between Q and H. This is similar to what we have done earlier in the modified Pull's method. And the third thing is that SHQ at time T is equal to 0 or known. And then since these are known, I1, I2 are also known. So you know the value of I1 plus I2. You know the value of 2S1 delta T minus Q1. So then you can use the equation 1 to compute 2S divided by 2 delta T plus Q2. And then next what you can do is that from the plot that you plotted here you can compute H, and from H you can compute Q. And then again repeating the steps that we did above. So you can generate outflow hydrograph. So this is very similar to the first method, very much similar to the method that we have already done. I will end the meeting and you can join again. So now we are going to do the problem number second, which is to route the following flood hydrograph through the reservoir. And this is the same which was example first here. Here we solved this by using modified Coles method. And now we need to solve this by using Goldfish method. So the initial conditions are given that the reservoir has an elevation of 100.6. You are also given the time and inflow. So the first thing that we need to do is the time step is again you calculate 6 minus 0, 12 minus 6, it's 6 hours. And if we convert it into the seconds, so this will be 6 into 60 into 60 seconds. This will be 0.0216 into 10 is power seconds. So second thing is to now prepare Q versus H plot and 2s upon delta T plus Q versus H plot. So once these two are plotted, then we can proceed. I will share the Excel sheet. So you are given the elevation, you are given the discharge and storage. So first of all, we will calculate 2s, which is storage upon the time, which is 0.0216, and then you have to add the discharge value. So this is going to be your 2s divided by delta plus q. And now we need to plot this. On the x-axis, we plot 2s upon delta t plus q, and on the y-axis, we are going to plot the elevation. So this is going to be our first plot, and second plot is between q and h. So on the x-axis again, you need to, sorry, this time we need to plot on x-axis is the discharge, and on the y-axis again, we need to plot the h. So these two are the plots first you need to create, and then we can proceed with the calculations. So here are these two plots. This one is 2s upon delta t plus q versus h, and this is h versus q. So yeah, we can start at time t is equal to 0. Your h is given, which is 100.6 meter. And if we look into the figure, if you have a stage of 100.6,
sorry, 100.6, which is nearly here, and you can compute the value of discharge. So this is going to be roughly 12 meter cube per second. So your Q value is 12 meter cube per second. So 2s upon delta T plus Q is going to be equal to, so if you put the values, it will be equal to 340 meter cube per second. So now from the equation, we know that 2s upon delta T minus Q will be equal to 340 minus 24, which is equal to 316 meter cube per second. For the first time interval, I1 is 10, I2 is 30, Q1 is 12. So if you look into this, I1 and I2 are here. So now we use the equation 2s plus Q 30 at second time step is going to be I1 plus I2 plus 2s plus delta T minus Q at the time step 1. So you put the value of I1 10, I2 is 30 plus 2 into 12, which is your discharge value. Upon delta T, you know value of 0.0216 minus the value of Q, which is, sorry, we know this value. This value is 316. So you get a value of 40 plus 316, which is 356 meter cube per second. So now you know the value of 2s plus delta divided by delta plus q is 356 for this time step. You go here and you can take the 256 will be roughly here. From the plot, you can compute the value of h. And this h comes to be equal to 100.74 meter. So once you calculated the value of h, you go to the second plot and 100.74 is roughly here. And this will be your discharge. And this comes out to be around, the value is around 70 meter cube per second. So once you compute the h and q, so for the next time step, interval, so 2s upon delta t minus q now will be, for the next time step, it will be, earlier it was 356 minus, we had to subtract 2 times the discharge, that comes out to be, and this is going to be 322 meter cube per second. And similarly, now after this, you will take the value of I1 and I2, Q1, and then compute this. After this, you again compute the value of H. So you have to repeat this process and until you get the Q outflow. So this will be your outflow discharge hydrograph. So another method that we have is called, this is an, I will just brief about this method. So this is called standard fourth order Runga-Kutta method, RK method. So it's also solves the continuity equation numerically. So this RK method is a numerical method. which you may have read in the numerical methods. So let's say you have an equation ds by dt, which is your continuity equation. So ds, we can write it as area function of h into dh, and then we can write dh by dt as I of t minus q of t divided by a of t. This we can call f of t comma h. So initial conditions, again for this also we need to know initial conditions. T at t naught 0, we need to know I naught, q naught, h naught, and storage s naught. Then hi plus 1 will be hi plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4 into delta t. And this k1 is going to be function of ti comma hi. K2 is going to be the function of ti plus delta 2 divided by 2 comma hi plus 1 half of k1 into delta t. Similarly, the k3 will be function of ti plus delta t divided by 2 comma hi plus half of k2 times delta t. K4 will be function of ti plus delta t comma hi plus k3 times delta t. So starting from the known initial conditions and knowing q versus h and a versus h, so we can route the initial hydrograph at the upstream and calculate what will be the hydrograph at the downstream. Hmm. Now we now go to the another method. So this is actually earlier what we read it was the hydrological reservoir routing methods. Now we are going to go through the hydrological channel routing. So in the hydrological channel routing, we will go through the Muskingum's equation. So in this equation, you assume that there are two components of the storage. One is the wedge storage, another is the prism storage. So this is said to be the function of inflow, and this is said to be the function of reservoir elevation also. So using this principle, you can get the storage equation, which is k times x I to the power n plus 1 minus x q to the power n. So this is called storage time constant. This is a weightage factor, and this is constant m. So this Muskingum's equation is it is actually the same equation, but your value of m is 1. So the equation becomes k xi plus 1 minus x into q. So this is your Muskingum's equation. And the important thing is the estimation of k and x values. So delta s we can write it as s2 minus s1. This is going to be I1 plus I2. We know this equation from the continuity minus q1 plus q2 upon 2 into delta. So we can use these two equations to find the value of a and x. we can solve a problem on this. Before solving problem, uh, so what we do is in this cases we develop uh, S versus T plot, and then after this for different values of X, we plot S with above plot, and if it's linear, then the X that you have chosen is correct. And once X is chosen and X is computed, then we can calculate the value of K by simply inversing the slope of the straight line. I think it will be clear through the problem only. So now let's say we have to estimate the values of K and X applicable to reach for use in the Kingdom's equation. You are given the time, inflow, and the outflow. I will share the X. Now, so you are given time, inflow, and you are given the outflow. So the first thing need to do is to compute the inflow minus. Next thing you need to do is to compute the average I minus Q, and this average I minus Q is simply you take the mean of two consecutive time steps. Then you compute the delta S, which is going to be the average I minus Q into delta T. And your delta T in this case is again 6 hours. This is going to be your delta S. So now let me first plot these three. So this is your inflow. This is your outflow. This is your time step on the x-axis. You can plot this here. So now you have done is what is you calculated the difference of inflow minus outflow, which is the change in storage. Then you computed the average storage, which is by taking the mean of two consecutive time steps. And then you computed delta S, which is simply multiplication with the time, which time step, and time step was in our case 6 hours. Now you need to compute the storage. So anyone having any idea how we can compute the storage? Any idea? Anyone? So if not, then let me So S is, let's say we start with the storage 0 at the time t step. At the second time step, we will be going to have a storage of 42. And then at the time step 3, the storage will be the storage that we had at time step 2 plus 156. So it is just you are calculating the cumulative cumulatives of delta S. And now we can use the Muskingham's equation, which is x into I plus 1 minus x into q. The important thing is here that we have to decide, we have to start at some value of x first. So let's say I take a value of 0.35, and now let's say we use the equation, which is x, which is 0.35 into I, which is here inflow, plus 1 minus x, which is 0.65 into the value of q, which is 5, and then you plot this. So once you compute this, so this is going to be your S value. So Muskingham's equation gives the value of S, and this is for 0.35. So now let's say we plot the storage and we plot the values of this X. We analyze how it looks. Yeah. So the thing is that the whole idea on this Muskingham's equation to compute the K value of K and X is that the difference between these lines becomes very less and it appears to be a straight line. So this is in case of value of X is 0.35. Now we can choose the value to be, let's say in this case it was, so now we can choose the value of 0.3. So this will be 0.70. And if we plot this one also, so this is, so the lines are getting a bit closer as compared to 0.35. So we can go with the 0.25 value also. This will be, and if we plot S versus X, this is, yeah, so the lines are very close to each other. So we can roughly take value of X to be 0.25, and we can add a trend line to this display equation on the chart. Yeah, so this is the best fit line to this equation, these data set points, and the value of X comes equal to 0.25, and similarly the inverse of the slope of this line will be our value of K. Any doubts on this? So your X comes out to be 0.25, and the K is the inverse of the slope. So yeah, the K value in this case will be 400 divided by 30, and you get a value of 318.3 hours. So any doubts on this problem? If not, then I will go to the next topic, which is then using the same equation for the routing. Now we can use write the above equation as plus 1 minus x q2 minus q1. And same thing we can express this is from continuity equation that we have. Now you have equation 1 and equation 2. So if you compare 1 and 2, we get q2 equal to c naught q2 c1 I1 c2 q1, where c naught is minus kx plus 0.5 times delta t, k minus kx plus 0.5 delta t. Similarly, c1 is kx plus 0.5 times delta t, k minus kx plus 0.5 times delta. C2 is k minus kx minus 0.5 delta t divided by k minus kx plus 0.5 times delta. So also we can write the same equation, this q2 as q1 plus b1 minus I1 q1 plus b2, where your b1 is delta t upon k into 1 minus x plus 0 point delta t. B2 is delta t minus kx. So we will do a problem on this. You have to route a flood hydrograph where your reach, your K and X are given at the start of the inflow. The outflow discharge is 10 meter cube per second, and your time and inflow is given. So we know that the K value is 12 hours and 2kx is into 12 into 0.2, which is 4.8 hours. So it should be noted that your time step delta t, or what we use in equation, it should be greater than 12 hours and it should be, sorry, less than 12 hours and it should be greater than 4.8 hours. But delta t is 6 hours, so it's okay now. We can proceed. Yeah, so yeah, C naught is minus kx plus 0.5 times delta t divided by k minus kx plus 0.5 times delta t. So if you put the value minus 12, 0.5 into 6 divided by 12 minus 12 into 0.2 plus 0.5 into 6. This comes out to be 0.048. Similarly, your C1, uh, equation for C1 is kx plus 0.5 times delta t divided by k minus kx plus 0.5 times delta t. So if you put value, this one is roughly equal to comes equal to be 0.523. So, sorry, this one is equal to be 0.429. Now for the C2, which is K minus Kx. K minus Kx minus 0.5 times delta T divided by K minus Kx plus 0.5 times delta T. You can put the values. This now is equal to 0.523. So for the first time interval, which is 0 to 6 hours, I1 is going to be 10, I2 will be 20, Q1 is to be 10. So Q2 will be C naught I2 plus C1 I1 plus C2 Q1. So if you put the values, your C naught is 0.048, I2 is 20, C1 is 0.429, and your I1 is 10 plus C2 is 0.5253, and the Q1 is 10. So you get a value of 10.43 meter cube per second. I will show the all calculations in the Excel. This is problem 4. So yeah, so this is the first column. This is 0.048 of I2, 0.429 of I1. And then these are coefficients. Your third term of the Muslim's equation will be 0.523 of Q1, and then you compute the value of Q. We plot the first time and inflow graph. So this will be, you can start with here. This is going to be 0.048 into the value of this. Then we start with here, which is 0.429 into the value of I1. So if this is I1, this is going to be your I2. Then your value of Q1 is going to be, I think we were given the value of Q. No. Yeah. So the value of Q is, you can start here. It's initially it's going to be 10. And then, so this is going to be 0.523 times the value of Q here. And here you can calculate the value of Q by adding these three terms. It's 10.48. So this is, you have to drag it down. This is going to be your outflow. Now we can plot the same thing. Insert the plot. Yeah, so this is going to be your inflow, and this is the outflow you have generated using this equation. And you can clearly see there is an attenuation in the peak, and there's completely lag when this peak has been achieved. So any doubts on this? So if not, then I will give you a bit recap of Clerk's method of routing. Before that, let me revise this one. So what we did is we first tried to estimate the values of k and x in the Instingham's equation. Then we computed the value of q2 by taking the equation here plus c2 q1. And in this equation, we were given the value of I2, I1, and Q1. We computed first C0, C1, C2, and then we computed the Q2. Now, another method is called the Clerk's method. Clerk's method is also used to route the channel. So, so it overcomes the limitation that's the absence of the information on storage properties of the catchment. So basically what we assume here is the storage is linearly dependent on the discharge, and I minus Q, is an equation ds by dt. Then I minus Q is, if you put the value of Ks, K is a constant, it will become dq by dt. So K is nothing else but the difference in I minus Q upon dq by dt. So the procedure is we first know the values of K. Then for x is equal to 0, that's the case of linear reservoir. The I is calculated, which is AR into 10 raised to 4 divided by 3600 into delta T. C, which is the time of concentration, change in time of concentration. This is AR upon delta T C meter cube per second. Then we use the same equation that we had earlier in the Muskingham's equation method. This is Q2 is equal to C naught I2 plus C1 I1 plus C2 Q1. And yeah, so C2 is, sorry, C naught is 0.5 times delta T divided K plus 0.5 times delta T. C1 is 0.5 times delta T, K plus 0.5 times delta T. You compare here, C naught is equal to C1. And C2 is K minus 0.5 times delta T divided by K plus 0.5 times delta T. So this equation becomes then, if C naught is equal to C1, so it becomes Q3 is equal to 2 times C1 I1 plus C2. So, but yeah, important thing is the hydrograph that you generate here after routing is an instantaneous unit hydrograph. And from that instantaneous unit hydrograph, you can develop your own hydrograph that you are required at that cross section. So, yeah, I'm going to stop the meeting now. If there are any questions, please, you're free to ask. So if not, then I'm going to stop the meeting. Thank you.